Hello, and in this question here, we're asked to determine the initial percentage of uranium-235 on when the Earth was initially formed. Okay, so how do we go about this? Well, we're told in the question, okay, that the current percentage of uranium-235 compared to uranium-238, well, as a fraction, it's going to be 0.072, and as a percent, it's 0.72%. Okay, and this is equal to the percentage of uranium that is of the isotope 235. And just for ease of notation, okay, I'm just going to say uranium 35, and we just implicitly assume there's always a 2 there. And this will be divided by the total number of uranium atoms, which is the number of uranium 235 plus the number of uranium 238. Okay, so we know what this quantity here is. We can since the number of nuclei as a function of time is equal to the initial number of nuclei times e to the power of minus lambda t, and lambda is the decay constant, which is equal to the natural logarithm of 2 divided by the half-life. So we can use this to actually try and gain some information here. So this is equal to the initial number of uranium-235 times e to the power of minus lambda 235 t, all divided by the initial number of uranium-235 times e to the power of lambda 235 t plus the initial number of uranium-38 times e to the power of minus lambda 238 times t. Okay, cool. So we have some formula here. What can we do here? So we need to do some manipulation here. So we can factor out the initial number of uranium-235. Okay, so we get, well, so that's the numerator remains unchanged, and the denominator becomes so the initial number of uranium of 238 divided by uranium-235 times e to the power of minus lambda 238t plus e to the power of minus 235t. Okay, so we have this quantity here, this here cancels, and we're just going to say that well, this is equal to 0.072, and we're just going to say that this is x, just to make the algebra just more tidy. So what can we do here? We want to try and find this quantity here. Okay, so the ratio of the initial number of uraniums 238 to 235. So we can do some manipulation again and get that N038 over N035 is equal to well, that's equal to e to the power of 235t divided by x minus e to the power of 235t. So yeah, there's just some algebraic manipulation there. So I've multiplied this side up here and brought this term to the other side of the equals, and I should have an E238 here. Okay, so what did I do again? I divided the right hand side by the numerator by x and multiplied the left hand side by the denominator and brought the underlined term in red over to the right hand side. Okay, so this is what I have, and now I can multiply everything by e to the power of plus lambda 38t. Okay, so if I multiply this, I'll bring this over to the other side, and I'll get e to the power of lambda 38t. Okay, so let me do some more manipulation here. I can factor out this here. Okay, so I can get and then I can factor it out and then multiply it the same step with this here. So we can get e to the power of lambda 38t minus lambda 35t. Oh, whoops, I changed color. Sorry about that. This is just algebra, basic algebra, and it's 1 over x minus 1 then, and 1 over x minus 1, you can just rewrite that as 1 minus x over x. So we get a formula for the ratio of the initial ratio of uranium-38 over uranium. Oh no, sorry. This would be. No, sorry, that's correct. So the initial number of uranium-238 over uranium-235 is e to the power of lambda 38 minus lambda 35 times T times 1 minus x over x. So we know x, we just need lambda, the two lambdas, and T. Well, T told in the question is 4.5 times 10 to the power of 9 years. Okay, we're told that, well, we're going to use table 38.1 to get lambda 38 and lambda 35. So lambda is equal to the natural logarithm of 2 divided by the half-life. The half-life of uranium-238 is equal to 4.46 times 10 to the power of 9 years. And the half-life of uranium-35 is equal to 7.04 times 10 to the power of 8 years. So we can sub into the formula for lambda for the decay constant to get the decay constant of uranium-238 is equal to 1.5541 times 10 to the power of minus 10 years. And the decay constant of uranium-235 is equal to 9.845 times 10 to the power of minus 10 years. Okay, so that is all that sorted. So we can sub into the formula to get this expression here. So we get that just by subbing in with the calculator. The initial number of uranium-38 divided by the initial number of uranium-35 is equal to 3.1975. Okay, so how can we use this? Well, maybe I should have started with this, but the initial number of uranium-30, the initial ratio, okay? Okay, so it's the initial ratio that we're trying to find is the initial number of uranium 235 divided by the initial number of uranium 235. Well, this is the total number of uraniums initially. So that's the initial number of uranium 235 divided by the total number of uraniums. And this is what we're trying to find. And we can again do some manipulation to say that this is equal to this quantity here. Yep, it's equal to that. We can cancel this expression here. And what you know, this here is what we calculated up here. So we can sub that in and get that the initial percentage, which we're just going to call y, or the initial ratio or percentage, is equal to 0.238. Okay, or that means it was 23.8%. Okay, so that's the solution to the question, and thank you for listening.